Our first speaker is Nagesh Gupta, who's going to talk about semantic segmentation for scene understanding algorithms and implementation. Nagesh is the founder and CEO of Auviz Systems. Prior to Auviz, he started a company called Terray Systems that made FPGA design tools, which was purchased by Cadence, and he was sentenced to 3 years of hard labor at Cadence. When he left there, he started Auviz Systems, and what Auviz does is develops middleware IP to accelerate algorithms, essentially computer vision algorithms, onto FPGAs. He holds a MS degree in electrical engineering from the University of Kansas and a BS from BITS in Pilani, India. Thank you, Nagesh.
Thanks for the introduction, Vin. Good afternoon, everyone. So I know there's been a lot of deep learning talk during the rest of this, the past couple of days. So I'll try to minimize the amount of introduction that I give here and get right into the material. So the topics for today, I'll briefly introduce you to Auviz Systems and semantic segmentation, go through a quick survey of techniques that have been used, that have been popular for semantic segmentation. We'll go through a technique called fully convolutional network. This is a technique that comes out of Berkeley. In fact, it was created by the same guys who created Caffe and who presented the tutorials yesterday. Talk about the implementation architectures and the results for this particular network. We will compare FPGA and GPU implementations, just give you a little overview of how and what can be done on the FPGA versus what can be done on the GPU, and give you some references. So my company, Auviz Systems, we are an independent software vendor, and we specialize in implementing and optimizing algorithms. We have created 3 different sets of algorithms for the FPGAs. Auviz CV is a collection of computer vision algorithms. Auviz LA is a collection of BLAS algorithms. And again, all of these algorithms are completely optimized for the FPGA. So we've taken the OpenCV algorithms and the list of OpenVX algorithms, and we basically re-optimized it for the FPGA. And these are provided as with an OpenCL kind of an API. So essentially, you get to use the FPGA as if you're programming on the CPU or the GPU. That's kind of one of the key things that we did here from a use model perspective, is provided these algorithms so that it is much more usable and usable by software programmers. The third library is Auviz DNN. Auviz DNN is a library for you to create convolutional neural networks on the FPGA. So we also develop applications in computer vision, linear algebra, deep learning, and so on and so forth. These might be applications that are based on the libraries that we provide, applications that might be specific to our customers. And if you have not already, I would certainly encourage you to come over to our booth here at the show and stop by and take a look at the semantic segmentation algorithms running on Xilinx FPGAs. Moving on, image classification. I think nothing new here. So with image classification, you're essentially taking an image and trying to label the image, right? And today, I mean, especially after the last couple of days, that CNNs are used for doing image classification. And when you're doing image classification, one of the things that you have to keep in mind is you want to make sure that you've cropped the image appropriately, and that's when you're going to get the appropriate label. So that's image classification. All of us know about this. And now getting into semantic segmentation, how is this different, right? Now with image classification, you are essentially, adding one label to an image, whereas with semantic segmentation, you are basically classifying all of the pixels in your image and adding as many classes as you have in your network, right? So for example, in this particular image, you've classified the pixels into the giraffe, into the tree, into the earth, and sky, and so on and so forth, right? Now, the number of classes obviously depend upon, what exactly your implementation is. You could have a 2-class network, you could have a 10-class network, and that's the number of classes that you're going to get. So now, how is object detection different from semantic segmentation, right? So in object detection, you're basically looking at drawing bounding boxes. So for example, the same figure that I showed you in the previous slide, you're taking the giraffe and you're basically going to draw bounding boxes and say, now this is a giraffe and this is a tree and so on and so forth. Whereas with semantic segmentation, you've basically classified the pixels. So you're doing a lot more processing when it comes to semantic segmentation. So obviously, this is like a very interesting technology here. And so given that, this is very useful, there's been like a lot of applications that use semantic segmentation. So for example, you have free space detection. So this is a automotive application. You're trying to determine where is the free space when you're driving the car. How is the computer in the car going to determine where the free space is, and that's a 2-class network. Now, some other interesting applications of semantic segmentation, you can in fact do monocular depth estimation, right? And another kind of obvious application is boundary prediction. So you can figure out the boundaries of the images or different parts of the image in your picture. Now, given you have so many applications, there's been a lot of research that has happened with semantic segmentation, and what you see here is a survey of different methods. And what we have here is like number of research papers that have been published, and the SIFT flow pixel accuracy. So obviously you want to get higher the pixel accuracy. That's a better technique. And some of the earlier techniques, obviously, they were not based on convolutional neural networks. And the technique that we are going to be discussing today in a little more detail is based on CNNs, and that is, like I said, it was the inventors were the same people who presented Caffe yesterday in the tutorials. So they are the developers of Caffe who presented this particular technique. It's called fully convolutional networks for semantic segmentation, and it gives you a pretty good accuracy, SIFT flow accuracy of 85.2%. So let's kind of look at what was the motivation. How did the authors come up with this particular technique, right? Now, if you look at classification networks, and this is a classification network that might be familiar to a lot of you. It's AlexNet. It is 2012 ImageNet competition winner. So if you take this classification network, just take a look at what happens to a picture as you go through the classification network, right? As you go through like different stages of convolution, right? There are two things that are happening in the classification network. So the first thing is that you're going through different stages of convolution, and in the stages closer to the left, right, your image is on the left-hand side, your image is going from left to right, right? Stages closer to the left-hand side, closer to the input, you basically still have a lot of local high-resolution features still remaining in your outputs of the early stages of convolution. But then as you go to the later stages of convolution, you have a lot of global semantic information, but a lot of local high-resolution information is all lost, right? So that's one thing that happens. And then the second thing that's going to happen is there's subsampling as you're going through convolution stages. So what the reason for subsampling is you essentially want to reduce the amount of processing that you have to do. So that's one thing. And then you also want to like actually increase the size of the receptor there. And so in the case of AlexNet itself, by the time you've gone through all the stages of convolution, it is 32x smaller. The image itself is 32x smaller. So that's the classification network. And so what the authors did, what the inventors did is they basically took the classification network and modified it in order to get to semantic segmentation. So in this case, what they have done is they have the classification network, the final 3 stages, they have these fully connected layers, which is nothing but like kind of like a matrix vector multiplying the final 3 layers. So with that, you're going to get like a label at the output. So what they did is they took off those fully connected layers and they convolutionized those 3 layers. And by doing that, what they could achieve is you could now get like a heat map at the output as opposed to like a label, right? So now the idea is basically to make use of the heat map and then try to get to semantic segmentation itself. So what is semantic segment? What is this network trying to do, right? I mean, so you've got multiple convolution layers, and then they added this thing called deconvolution. Now deconvolution is nothing but it is very similar to convolution. It's kind of convolution with upsampling, right? As we as we went through the network, right? I mean, there was a lot of subsampling that was happening. We started off with like a image size of, let's say, 224 by 224, and we ended up with an image size which is much smaller, which is 32x smaller, right? So now what deconvolution does is it kind of upsamples the image back again, right? And then there's a classifier. Right? So now one of the things that that happened is like as you went through the different stages of the network, you went through subsampling, and because of subsampling, you lost a lot of pixel accuracy, right? So the next thing that the authors did is basically they added this thing called skip layers, right? Now skip layers, what it does is it kind of makes use of some of your early stages of convolution, the outputs from the early stages of convolution, and it combines them with your final output so that you get better resolution. So in this case, what you see here is you see the input image on the left there, the bicyclist, and without any skip layers, that's the stride of 32, and you see the let's see if I can use the laser pointer here. Okay, doesn't seem to work. So without the skip layers, that's the stride of 32, and then with 1 skip and 2 skip layers, as you've added those skip layers, you see how it has gotten closer to the ground truth. So that's your segmentation with 2 skip layers. It's called with the stride of 8, and that's pretty close to ground truth. So now kind of getting into what are very basic things, right? I mean convolutions. So with a convolution, you're basically taking a window of say k by k, filtering it, and going through the convolution operation itself in order to get 1 pixel. And to distinguish this from deconvolution, right? I mean, deconvolution is basically the reverse of that, right? So you're essentially taking 1 pixel and you're filtering it again with like kind of you're doing multiplications with a k by k filter and adding them up, and you're getting back a k by k region from 1 pixel, right? So very similar from a mathematical perspective. You're getting an upsampled image at the using deconvolutions here. So now let's look at some of the implementation results here. So these results are from the paper itself. So John Long and Evan Schellhammer, they published these results on the GPU. They were using Tesla K40C GPU, and what they have presented here is results which are based on intersection over union. So intersection over union is basically a metric used to measure the effectiveness of semantic segmentation. And if you see, it is essentially what it is trying to do is it is trying to see what is the overlap, right? I mean, so when you've actually segmented it manually versus when you're segmented it using your algorithms, it is trying to like actually map out and get to the overlap. And so closer to 100% is the best semantic segmentation here. What we can observe here is that FCN, a fully convolutional network, which is based on VGG16, has much higher IOU compared to compared to an AlexNet or a GoogleNet even. But obviously, it takes a much longer time. So it takes on the K40C itself, it takes 210 milliseconds. Now, these results are for excuse me. So these results are for the without adding any skip layers. So when you add the skip layers, the accuracy actually improves significantly, like I was showing you in the previous slide there. Now let's look at the FPGA implementation, right? So if you guys have done a lot of GPU programming, I think GEM is like used very commonly in GPU architectures. So you pretty much would implement convolutions, deconvolutions, and so on and so forth by mapping your data onto GEM. So that can be done on the FPGAs as well. But what we found is that it requires a lot of data remapping, right? So because you want to map your convolutions and deconvolutions into GEM, that itself takes a lot of remapping, and remapping gets expensive, right? I mean, you're basically doing a lot of memory data fetches, and your data fetches are not local, so you're basically doing a lot of page misses and moving around quite a bit. So so remapping gets expensive, and so just doing native convolutions actually works out much better. And so you would just implement both convolutions as well as deconvolutions using the convolution kernel itself, because like I was showing in the previous slide, deconvolutions are actually very similar to convolutions. And with convolutions and deconvolutions mapped into convolution kernels, you would get much higher performance there. Now, let's talk a little bit about what's the performance and what's the resource utilization and performance that you can get out of FPGAs. So today today for FPGAs, OpenCL is actually catching up to be like a very good use model, because it provides the users a use model which is very similar to like the GPU or the CPU kind of a use model. You're just calling APIs in order to implement different algorithms and so on and so forth. And with OpenCL, you get the same thing. I'll talk a little bit more about this in a couple of slides, but want to just introduce that concept over here. Tell you that both Xilinx as well as Altera, they do provide tools for doing OpenCL. And when you're using the OpenCL kind of a design flow, for example, Xilinx SD-Axle design flow, there is like certain infrastructure blocks that you would require, right? I mean, depending upon whether you're creating an accelerator card which is going onto your Linux box, or whether you're using accelerator which is using an SoC kind of a part, right? So it depends on that. But if you're going to create an accelerator for a Linux box, right? I mean, you have like a PCIe and a DMA kind of infrastructure blocks that you would require, and in all cases you would require memory interface kind of infrastructure blocks. So once you take away some space on the Xilinx FPGAs for these kind of infrastructure blocks, you still have about, I'd say about 65 to 70%, maybe slightly higher, that's left out for you to create the kernels itself. And so in a part like say a Xilinx Vertex 7 690T, you can achieve, you can get about 1024 to 1500 kind of max. This is in reality, although it's got a lot more max, you really cannot make use of it once you start creating all the data flow and other structures that are required. It's hard for you to access all of the routing resources. So with that, a good design can then achieve about 400 to 600 gigaops. Maybe slightly higher, maybe slightly lower, but that's kind of the range that we think is achievable in a Vertex 7 kind of an FPGA there. So getting a little bit more into the use model itself, right? I mean, the use model is very important, right? Now, if you went to the cafe tutorial and so on and so forth yesterday, or if you have used GPU programming itself, you'd see that if you have to create a convolutional neural network on the GPU, all you're doing is you're basically calling the GPU, calling the making use of the CUDA libraries, and you're doing convolution forward or fully connected and so on and so forth, and so you're creating different layers by doing this, right? So makes it a lot easier, obviously, for a user who's trying to create CNNs. You are focused more on creating the network itself and not focused on how do you optimize it on the GPU, right? So that was very important, and so we want to make sure that we get the same use model, and this is in fact what's offered from my company, which is Auviz Systems. So we create kernels on the FPGA and provide a use model which is very similar to the GPU use model. So for example, you were doing the forward convolution by making a call on the GPU, and you're doing the same thing here on the FPGA. So getting a little bit more into the OpenCL use model itself, it's again very similar to how you would how you would do it on the GPU. So you would call the APIs and set the different parameters for the APIs, and that would then create the different layers. And the data can be passed from one layer to the next layer, or you can write it back into the DRAM and read it back. So that's a design choice that you would make. And the kernel itself, which is in binary format, that is not something that users need to worry about, because that's like been highly optimized for performance, and it's kind of tuned so that it can accept all the different parameters and so on and so forth. Don't need to worry about getting to the FPGA timing closure. Don't need to worry about going to the FPGA tools and so on and so forth. So we implemented the fully convolutional network on Xilinx Vertex 7 FPGA, and we used the technology Auviz DNN that we have developed. And in order to do semantic segmentation with 2 to 21 classes on a 500 by 500 image, you can achieve real-time performance, which is what's important. So we could achieve 30 frames per second on a Xilinx Vertex 7 FPGA, and projecting the performance to other parts, right? I mean, so the Xilinx has Zinc ultrascale part that is coming up. So that's with that you get 60 frames per second, and with like Kintex ultrascale kind of a device, you can get up to 120 frames per second. So which is important, I think essentially what this shows is that you can get to real-time performance on an FPGA for semantic segmentation. And again, this is not like an optimized network. It's a network which is basically a modification of the fully convolutional network. So quickly summarizing, where would you use an FPGA? Where would you use a GPU kind of thing, right? So the GPU, obviously, it's a very mature use model. They provide a very rich set of libraries. And when you want to do training, for example, you look at all the publications that are coming out of the universities and so on and so forth. They pretty much use GPUs because they've all, training, for training itself, GPUs have like a very good set of libraries, and they also provide the performance that is required for training. But GPUs have traditionally been higher from a power perspective, right? Although that's changing a little bit now. And also GPUs have been integrated well into infrastructures such as Caffe and TensorFlow and so on and so forth. So FPGAs, we are trying to catch up, right? So my company provides the libraries, and that's big help from a use model perspective. So we are trying to provide a very similar use model as the GPU. And for while GPUs have been used for training, for the FPGAs are actually a serious contender even in the data center for deployment itself. So for doing the actual inference, FPGAs are a serious contender. Power draw perspective, FPGAs have been like much lower in power draw, have been used very extensively for embedded applications. And we also provide a loose integration with Caffe. So that summarizes my presentation here. And I provided a few references for you guys, if you want to take a look at it, some interesting papers. Thank you very much, and I'll be happy to take some questions.
Thank you, Nagesh. We've got some hand mics. Questions from the audience? So Nagesh, I have one question for you. You mentioned that VGG16 is a better network for implementation. It seemed to have higher accuracy, but it looked like at the very end you used a version of AlexNet. Was it?
Yes.
Why did you make that decision?
So it's AlexNet is actually again from a performance perspective. If you see the performance of VGG16 on a K40 Tesla K40. The authors published 210 milliseconds for doing the semantic segmentation.
Much lower performance.
Much slower from a performance perspective.
Okay.
And so that's why we used AlexNet. But in fact, these networks today, the trend is basically about minimizing the networks. Mm-hmm. And you can actually achieve very similar performance by minimizing the networks. And then also the quantization is another technique that has been used. So what we have published here did not get through like the minimized network and did not get through quantization and so on and so forth.
So the beauty,
we expect much better results.
So the nice thing about this approach is you can iterate on the implementation and change the topology of the network to suit the particular end application and do that rather quickly. And improve the performance. Okay.
Yeah.
Questions?
Over here?
Yep.
Yes. To your left.
Yep. Right over here.
Here. Okay. I was wondering if you compared the performance under OpenCL to a straight RTL implementation. I'm curious what kind of inefficiencies are imposed in exchange for the ease of use of OpenCL.
So actually, that's a very good question. So I'll tell you one comparison point that we have, right? Microsoft actually published numbers on Altera Stratex 5 device. I think it's like a 480 or something. I don't remember the part number. But Microsoft published some results, and just for pure AlexNet itself, Microsoft published about 135 images per second, right? Now, Microsoft did that. They took like, I think, they had like about 20 odd RTL designers, worked on it for a couple of years, right? Now with OpenCL, of course, our initial implementations did not achieve that level of performance. We were like at about, I'd say about between 75 and 100 frames per second. But of late, we have actually been able to optimize it, and we are getting close to 150 milliseconds. 150 images per second. So we've been able to achieve the same performance. Or better performance, slightly better performance than what Microsoft had published.
And do you think the amount of optimization you did in OpenCL was similar to the amount that they did with RTL, or do you think you had to do more?
I would say that we probably spent lesser time. We spent a lot lesser time and lot lesser from a number of resources perspective, right? Because with OpenCL, this whole cycle of verification, for example, right? You have like a huge team that's actually doing RTL verification. So all of that goes away, right? And you don't have that, that extra 10 people trying to do the RTL verification, right? And also from a time perspective, it takes time for you to understand, how the tools work and so on and so forth. But once you get there, then you can actually do the implementation very optimally.
Thank you.
Thank you. Okay. Thank you, Nagesh, very much. Appreciate the talk.
Thank you.
See you at the drinks.
Yes.
All right.